Hello, in this video we're going to learn about trees and their representation. So the first part we're going to talk about tree terminology. A special type of graph called a tree turns out to be very useful representation of data. So let's see, a tree is a graph, but what's the difference between the graphs we've seen before and this graph? Well, this graph here is not closed, it's open. You don't have a cycle. So if this one was closed like this would not be tree. So as you see, tree can have a root and children or leaves. So let's see. Here is a definition. A tree is a cyclic, that means no cycle, connected graph with one node designated as a root of the tree. So you always have a root of the tree and the rest. So let's see here which of the following graphs are trees with root R. If a graph is a tree, draw it in a more conventional way. If not, say what property fails. So for A, this is the root. So the root is here, so it has 1, 2, 3 children or leaves. And that's the appropriate way of drawing a tree. So yes, this is a tree. And this one here, since you have a cycle here, this is not a tree. This one here is the root and it has 6 children. So yes, it is a tree. For this one here, if you see, if I can move this node here and this node here, we could draw it this way. So as you could see, this is, yes, it is a tree. So this is the only one not tree because of that cycle. So you always have to have a root and no cycle. So here a tree can also be defined recursively. If you remember in chapter 3 we covered recursive functions. So a single node is a tree. So for example, this cluster here is a tree by itself and this will be the node for it. Right here, and another cluster which have another tree as well, and you could have a nested one and one here and so on. So if T1, T2 and up to Tt are disjoint trees with the root R1 to Rn, the graph formed by attempting a new node R by a single arc to reach the R1 and R2. So again, and you need an arc to connect one root with the other cluster of roots. So the nodes R1, R2 are children, and R here is the parent. So the depth of a node in a tree is the length of the path from the root to the node. The root itself has a depth 0. So if I take this example here, this is depth 0, this is 1, this is 2, and this is 3. So this graph here, this tree, so this graph here has a depth of 3. The depth or the height of a tree is the maximum depth of any node in the tree. In other words, if the length of the longest path from the root to any other node, so the longest path can be this one here or this one here. As you see, 1, 2, 3. A node with no children is called a leaf of the tree. So this is leaves right here. And so all of these are leaves, the last node in the path. All non-leaves are internal nodes. So this is internal nodes, which you could be roots if you take this as one cluster. A forest is an acyclic graph, not necessarily connected. So you could have one tree here and another one here, and even if they are not connected, the whole thing is called a forest. Binary trees are those where each node has at most 2 children, and we're going to see in details binary trees. Each child of a node is designated as either the left child or right child. So here is left child, right child, left child, right child, and so on. A full binary tree, as seen in the middle, so this is a full binary tree here, occurs when all internal nodes have 2 children and all leaves are at the same depth. So all of them have the same depth. So this is full binary tree right here. These are very important structure in data structure course. So as you can see, this is left and right child. A complete binary tree, as seen in the right figure below, is an almost full binary tree. The bottom level of the tree is filling from the left to the right. So this is complete binary tree. So data structure, complete binary tree, all nodes in the last level area. All nodes in the last level are as far left as possible. So like this one. So let's see this example. Sketch a picture of each of the following trees. A tree with 5 nodes and depth 1. Full binary tree of depth 2. A tree of depth 3 where each node at depth I has I plus 1 children. So what I would like you to do is stop the video and try to sketch these trees. So a tree with 5 nodes and a depth 1. So here is the root, and depth 1, that means here is 1 root, and that means I need 4 children, which are leaves. So right here I have 5 nodes total, and depth is 1. For B, we need a full binary tree of depth 2. So full binary tree, just like this middle here, but the depth we want it to be 2. Here is 1 depth, and here is a binary, that means every node, internal nodes, will have 2 children, including the roots. So this is a full binary tree with depth 2. So here is depth 0, here is depth 1, and this is depth 2. So for C, we need a tree with the depth 3, where each node at depth I has I plus 1 children. So here is the root. Well, the root is depth 0. So I need to have I plus 1 children. That means 0 plus 1 children. So 0 plus 1, it will be just 1. So I need a 1 child. And this node here should have, so this is depth 1. And this node here should have I plus 1. If the depth is I, which is 1, should have 1 plus 1 children. That means it should have 2 children. And now I'm still in depth 2. We need depth 3. That means each node will have 2 plus 1, 3 children. Okay. Application of trees. So decision trees were used to solve counting problems in chapter 4, if you remember. We used decision trees there. And also by using trees, a collection of records can be efficiently searched to locate particular record or to determine that record is not in the collection. Similarly, files and folders stored in a computer. So if you look, there is a desktop, is one file, and then under desktop you have many files, and maybe one file is Math 2570, and under this Math 2570 maybe you can find videos file, and then maybe document files, and so on. So this is a structure just like a tree. So algebraic expression involving binary operation can be represented by labeled binary tree. So here is where we have, it says draw the expression tree. So as you see, what I have here, I have all of this added to 1, so addition 1. But let's think here, what is the measure thing? So we have parentheses first and then plus. So there is a plus, there is some parentheses, and this plus here you have a multiplication 4 and a z, and then right here this parentheses which is to the left here, you have a subtraction, and what we have is subtraction here, and there is 2 times x and 3 times y. For the next example here, as you see, I have 1, but it's subtracted from, this is the main binary operation, so everything in parentheses will go to the other side. So what I have 2, but minus, and now I'm in this bracket. So what I have here, the major binary operation is another negative, which is this one I'm talking about now. And then I have 3, and here parentheses, I'm dealing now with the 4 minus 5. So here is a minus, and 4, and 5. So this is how you draw the expression tree for some algebraic expressions.